Hi, everyone. Welcome to the 62nd session of the MedAI group exchange sessions. And this week, we have Christian and Pierre from Stanford here with us to speak about their work on using Stable Diffusion for medical imaging domains. Christian is a physician scientist, a radiologist with a clinical focus on thoracic imaging, and is currently a postdoc at the Stanford AMI Center, where he works on the application of deep learning for detection, diagnosis, and monitoring of interstitial lung disease and other thoracic pathologies. He utilizes large multimodal imaging and EHR datasets for this. Pierre recently graduated with a master's from Stanford ICME and will also get another master's from École Centrale Paris. And he's an ML researcher working with Stanford AMI with a focus on mathematical and computational methods for machine learning and deep learning. He has been involved at the AMI Center for the last 2 years, where he's developed NLP methods for domain-specific applications to radiology, as well as multimodal tasks along with vision models. So thanks so much, Christian and Pierre, for joining us today. Before we start, do you have any preferences on how you'd like to take questions? Is it okay for us to interrupt you, or do you prefer things at the end?
I personally would opt for taking them at the end of the talk because it keeps the flow going, unless you have something that is very pressing, or if there was a point that you really didn't understand and feel the need to ask. So then you can feel free.
Sounds great. Yeah, we can keep the questions at the end then. So yeah, without further ado, let me hand it over to Christian and Pierre.
Yeah. So first of all, thanks for the kind introduction and thanks for the invitation to present our work here. We are pretty excited about what we did. This has been a joint work from a lot of people at AMI, obviously, and in terms of collaboration, I'm very happy to also have Pierre in this talk, who did a major share of the work. And we're happy to talk about this now. So this will be about adapting pre-trained vision language foundational models to medical imaging domains. And these are our disclosures. We don't have any project-related conflicts of interest, but have received some research support. The rough roadmap for this talk is that I'll briefly go over why synthetic data for medical AI is interesting. Then we'll take a look into latent diffusion models, and then at the end, or towards the second half of the talk, we're going to talk about what we did to analyze the capabilities of the Stable Diffusion pipeline for these purposes. So I'm sure you all came across the great trend that is happening in social media right now. That you now have really powerful AI models that are capable of generating high fidelity images and can be controlled by just using text prompts. And here are two examples. One of them is a real image that I took at the Yosemite Park of the Nevada Fall, and one is a generated image. And you can see that these models do a great job in terms of lighting, in terms of texture, in terms of how the images are composed. And we've seen a lot of hype going on in that area because the kind of stuff that you can put in the image covers a wide range of scenarios of topics. However, if you try these models off the shelf for the generation of medical images, you might be a bit disappointed. These are two examples from the Stable Diffusion pipeline that has been released a few months ago. And if you just prompt these publicly available models for medical images, for instance, here we tried a photo of a lung X-ray, or a photo of a lung X-ray with a visible pleural effusion, then you might be disappointed because the content of this image is somewhat medical. So you can see how this is supposed to be a bone or a rib cage, but there are way too many ribs. This is nowhere near anything that could be considered a realistic human anatomy. And also the pixel distributions in terms of color and in terms of lighting, they are totally off when compared to, for instance, a chest X-ray. So maybe to take a step back, why it would even be interesting to have access to synthetic data in medical imaging. That's one thing that came up on Twitter quite a bit when we tweeted about this work, was the question, why do you even bother with this? So we tried to think of a few application scenarios where this is relevant, and indeed there's also some literature on this topic. And one thing where these models would be quite interesting is just in the setting where you have a heavily imbalanced data set, for instance, and you have some kind of rare disease that you want to model and come up with predictive models for this disease. Then one nice application scenario would to be data augmentation for that. And you might ask, okay, but we have other means of data augmentation. And I guess that's a fair point, but there are also other benefits of synthetic data. For instance, if you think about creating a multi-center study, and if any one of you has tried to do such a project, there's usually a large overhead concerning the anonymization process, the preservation of patient privacy. You have to care about a lot of regulations that are in place. And so it takes a very long time to be able to share data, which could, for instance, help you increasing the number of rare disease examples that you have for training your models. So that's another point, that instead of sharing the data directly with the concrete instances, you share a model that has learned the distribution of these cases and can reproduce synthetic examples. Another thing where this would be cool would be if we have models that know how to generate this data. We can also influence and try to identify factors that explain classification models, for instance. We have a cool example here that came out of a fellow from the Amy Center, Joseph Cohen. This is from his paper about giftsful nations, and that's a technique where you try to overemphasize a feature that was responsible for a classification decision that the model came up with. In this case, this is for cardiomegaly, so when the heart is enlarged, and you can see when you isolate this feature and try to make it more prominent, then you can also visually appreciate that the heart becomes bigger here, and you can also see that this affects the classification performance. So it would be a great factor for post-hoc explainability. And then, of course, if you can control the model output, it would also be great to show people exact examples of what you are trying to show. Instead of browsing a couple hundred cases, you can just create an example, and that could be very useful for teaching. This list is not exhaustive, of course. There are some other use cases you could think of, but for the sake of time, we'll go on and jump into the space of generative modeling. And of course, these diffusion models that have created a lot of hype recently, they haven't been the first generative models. I'm sure all of you who are listening and tuning into this talk are familiar with generative adversarial networks that have been used for many medical applications. Of course, you also know variational autoencoders. Maybe in the medical imaging domain, a little bit less known are flow-based models. And all of these models usually try to have some sort of bottleneck in there and try to learn the representation of the representations from the input samples, then compress them and try to decode them to create to come up with a synthetic version that is quote unquote inspired by the inputs. So in the past year, we have seen an explosion of the diffusion models that were on the last row of the previous slide that I just showed you. And you see a lot of big names here that have created a lot of fuss. For instance, DALL-E 2 from OpenAI, or the Imagen model from Google Brain. And what is common for these models is that you have diffusion model that does a lot of the heavy lifting for the composition of the image. And in a lot of and a lot of times these are also multimodal models. So for several reasons, this year is very interesting in the generative space and AI in general, as we've seen a real explosion of these models. And that's also something that got me more interested in that topic, and that's why I tried to find applications for that for my own research work. So the basic principle of a diffusion model that underlies all of these models that I've talked about in the last slide is that basically you try to invert a process where you start off with a natural image and you progressively, iteratively add small amounts of noise to that. And if you do that often enough, you end up with a completely random isotropic Gaussian distribution with the same dimensions as your input sample. And what you try to do is to revert this process by predicting what did the image look like before adding that noise. This comes with some nice attributes for this problem space. And in principle, what is created here is a Markov chain where the state of every image is dependent on the previous image. What is challenging in general for diffusion models, because they are iterative, so you have to do this a lot of times, and this can become quite computationally expensive. So when you have a diffusion model that operates directly in pixel space, you have a large matrix that you need to deal with if you're talking about an image, which comes with high computational costs. The paper that we're mainly talking about today lists numbers of 150 to 1,000 V100 GPU days. So it can become quite expensive. It's also resource intensive in terms of memory consumption. And then it's also slow. So to generate 50K samples takes roughly 5 days on one A100 GPU. And one A100 GPU, last time I checked, was about $1.5 per hour. So it can become quite cost intensive, especially if you are still experimenting how to best set up the model and you have to go through a lot of iterations of the model creation process. So one nice thing that happened was that people discovered that actually to create a good representation of an image, you don't actually need to model every single detail. And this is a nice figure that is included in in one of the main papers for this article. Oh, by the way, this QR code takes you to a Google document. You can also type in this link, where a lot of the papers that we're talking about here are linked, and you can take a look at them and read if you want to know more details. But basically, what this figure tells us is that we can reduce the information that is needed to display the image a lot, while still maintaining a high semantic fidelity to the original image. So a lot of the information goes actually into memorizing high frequency features that are not really relevant to display the main semantic features of the image. And the image becomes only distorted if you strip it away from really the last couple of bits of information per dimension, which is explained in this graph. So that is a bit of a challenge for diffusion models. They are likelihood-based models, and they have a tendency to do mode covering. So they try to mimic, they try to model all of these high-frequency details in an image, which makes them very resource intensive, as opposed to, for instance, GANs who display this mode seeking behavior, but also come with the downside that they are not capable of modeling distributions that have a lot of modes in them. So they tend to display mode collapse, for instance, which is a big issue with training GANs. And ideally for your generative models, you want to have a high fidelity to your original distribution, and you also want to have a high diversity in the generated images. That would be your ideal generative model. So one thing that is pretty interesting about this approach, this is from this paper, which I highly recommend taking a look into, from Rombach et al., from a research group in Munich. They proposed this model architecture of latent space denoising diffusion models, where in the first step, you try to eradicate a lot of these features that are not relevant for the semantic content of your image by incorporating a VAE, an encoder-decoder model that transforms your input into the latent space before actually performing this denoising process that I mentioned before. By this, the whole training process here becomes much more computationally efficient. And at the same time, you can still reconstruct images that are structurally very similar to the original inputs. So in these latent diffusion models that are proposed in this paper, and that are also the foundation for Stable Diffusion, for instance, there are three main components that we want to discuss today. The first one being the variational autoencoder. The second one is the component that takes care of the denoising process, which in this case is a UNet. And then there you can also condition the output, as we all know, either through text prompts, but you can also use images as an input, feed them to a domain-specific encoder, and influence the denoising process with that. So the first component that I'm talking about is the VAE. It has been trained on a perceptual loss and a patch-based adversarial objective during training. And in the way it was trained, it has the nice properties of enforcing local realism and avoids blurriness, which you often see when you do loss that is based on the pixel space itself, instead of a perceptual metric. The other thing that we need to be aware of here is that a lot of these large diffusion models that we see also incorporate downsampling before the actual denoising process begins. This factor varies a bit depending on what concrete architecture you're looking into, but it's also something that you need to keep in mind. The next part is the denoising process that I've mentioned before. So you try to create this Markov chain where you iteratively try to work from a piece of random noise towards an image that is that looks realistic. And in its essence, it's a series of denoising autoencoders, UNets in this case. On the last component, I'm trying to speed up here a bit because you will be quite curious how we actually came up with the medical images. Just trying to outline the basic components of this model here. Is a whole pool of different conditioning mechanisms that you could potentially work with to influence the denoising process. This works by modeling a conditional distribution, and the way you can do that is by, for instance, by feeding a text prompt to a domain-specific encoder, or you take an image, or you can also create some kind of semantic map and say, okay, in this part of the image, I want to have this object, and this part of the image, I want to have this object. So there's a lot of different application scenarios, and in the paper they also go over a couple of examples for that, which is kind of nice, and also one reason why you should be looking into the paper. So in this case, the objective is joint optimization of both the denoising network and as well as this domain-specific encoder. In the concrete case of Stable Diffusion, the downsampling factor that I mentioned for the VAE is a factor of 8, which is happening during training. The denoising network is a UNet, And for the domain-specific encoder, for the text-to-image generation, you have a fixed pre-trained clip text encoder that you're working with. All of these Stable Diffusion has been trained on the Lion dataset. Depending on the version, it has been trained on different parts of this big data set, which is basically just a web scraped data set of a lot of images and text image text pairs. And the results speak for themselves, so it's really fun to play around with this model. I'm sure everyone on this call has tried to get some and generate some pictures with it. So there's a large variety of images that you can create. Also, these images do really look realistic, so we fulfill both of the criteria for generative models that we want to have. We have a high diversity, we have high fidelity with natural images, and also the nice aspect of being able to control it through a text prompt. But still, we are at the problem of not being able to create medical images off the shelf. So we try to experiment with how we can best pull that off. And so we kind of approach this in a first principles approach by looking at the individual components, what they do, and try to influence them. So the first thing that we looked into was how well the latent space that the variational autoencoder that Stable Diffusion comes with preserves the medically relevant information in these images, because of the downsampling as well as because of the semantic compression that is happening in this variational autoencoder. I was thinking, okay, this might work well for natural images, but medical images are a different beast altogether. So I wanted to see, okay, if I just take this VAE, feed in images, feed in chest X-rays, and look at the reconstructions, how well are the images preserved? And I found that remarkably, right off the bat, right off the shelf, this VAE does an amazing job to reconstruct chest X-rays. Most of the features that are relevant for diagnosis are really well preserved. Some other nice detail is that a lot of the tiny text gets scrambled. So, but it's in this case it doesn't matter for us because we don't really need that. It's actually a pretty nice finding in terms of a possible anonymization procedure that you can use this VAE for. But really the main finding is that the contours of the ribs, the fine details of the installations, the general outline of the lung, the vessels, all is being pretty well preserved in these reconstructions. And that's why we said, okay, this model can probably be used to work with this VAE in place without having to worry about retraining a new VAE for it. And another level where we analyzed this was by taking a classifier, a DenseNet 1-to-1, that has been trained on original chest or on real chest X-rays for a variety of pathologies that come with the Mimics CXR dataset. And we tried to see, okay, I'm gonna feed in the original images and also the reconstructed versions of the images and compare the classification performance of the two. And what we found is that it generally preserves the classification performance well. And to our surprise, we also saw that in some cases, there's a slight increase in performance for the reconstructed versions, which was a surprise to see. And one possible explanation for this would be that this reconstruction process through the semantic compression removes a lot of features that are unnecessary for the classification process. So that was something that was nice to see. Okay, I'm gonna switch over to Pierre because that is a lot of the work that he has been doing. I'm gonna stop sharing my screen and Pierre, you can take over.
Yep. You should see the slide in full screen. Yep. Okay, great. So yep. So following what Chris said, so we have the vanilla stable diffusion model with the variational autoencoder. So we're happy with that. The text encoder. Do you hear me well, by the way? Is the great, amazing.
Yes.
The variational autoencoder, the text encoder, and the unit. These are the three components. Chris did these amazing experiments where we see that the variational autoencoder, which has a task to map the image to a latent representation that like shrinks its number of dimensions. He showed that well, this variational autoencoder is also like very good for the domain of radiology and the medical images. So that's like a super good thing. And it means that we can basically keep this variational autoencoder frozen for the follow-up experiments. So if we take the vanilla stable diffusion model and try to output the radiology images, as we saw, it's not super great. But maybe as this variational autoencoder frozen is good at reconstructing medical images, we could leverage the UNet or the text encoder or both, further fine-tune them and come up with a new version of the stable diffusion model that is better at generating radiology images. And so to further investigate in this direction, what we could leverage to improve the stable diffusion model generation capabilities in the radiology domain, we had a look at the UNet and the text encoder themselves, see how well they can tackle such data. And so starting, for instance, with the text encoder, that's a little bit what we had in the original stable diffusion work. That is to say, the clip text encoder, which was trained on this task where you are trying to have like joint representations of images and texts. And this clip text encoder is like super great. It was trained like on general data scrapped from the internet, so images of cats, dogs, not especially medical images. But it is very good at learning like good text representations of these general images. On the side, of course, there has been like a lot of research in the text encoder field, and you have like a bunch of in-domain text encoders, such as PubMedBird, ClinicalBird, and so on, that are supposed to have better representations of medical prompts. So maybe we can leverage that and compare that to the CLIP model. What we did first is similar to the experiments with the variational autoencoder, is to try to assess whether this CLIP text encoder, which is in the original stable diffusion work, is good with medical prompts. Is it good enough? Is it maybe very bad, in which case we're going to need to change it? Otherwise, we won't be able to condition the generation of images on nice medical prompts. And so that's what we needed to assess. To do that, so just like just as a detail, but you have all these text encoders and you have like various methods to extract the embeddings from them. So maybe you have a prompt and you would like to work with a document level embedding, in which case you could use, for instance, the CLS hidden representation, or maybe you could average the embeddings of each token to get this document level representation. Maybe you could not take the output of the pooler layer, but of the last hidden transformer block. So that's also like something to keep in mind when using all these text encoders, is that we can get like embeddings from them in a different ways. And sometimes, well, some embeddings are better than others, depends on the task, depends if you want to work at the token level or the document level. How do we then assess the quality of such text encoders for the medical domain? Well, we try to think of two ways, one that is very quantitative and also one that is like visual. And to do so for like, for instance, for the quantitative part, we had like our text encoder that we wanted to assess for the radiology domain. We had like all these impression sections, especially from the mimic dataset, but one could work with other datasets. But like we had like all these impression sections. And so we could, like, using the text encoder with an extraction method. The extraction method, as I said, well, you have a bunch of different ways. You can take like the last layer representation or other things. You can get like for each impression section an impression embedding. let's say we're going to simplify work at the document level, but you can this way with each text encoder get like impression embeddings that correspond to these impression sections. And then for a set of impression sections that can correspond to all mimic radiology reports, for instance, you can get like similarities if you just take like the dot product between the embeddings of all these impression sections. And so that's a little bit like the whole formula, but well, I can explain simply. That's not super tricky. Like you can take like a report, its impression section, and well, using these similarities, find the reports that are the closest to this report in the embedding space. So you compute like the embeddings of all the reports, you look at the similarities, and you can therefore retrieve reports that have a very similar embedding. And then using these Chexpert labels. So the Chexpert labels, it's only for like the chest X-rays, but like yeah, it says like is there like such abnormality in there, like pneumonia, pneumothorax. You can leverage like these Chexpert labels to represent maybe the general meaning of an impression section. And so putting all of this together, you can take an impression section, compute its embedding, get like all the most similar impression sections and look if they have like the same Chexpert label. What you are hoping is that an impression section that describes pneumonia will be very similar to impression sections that are also describing pneumonia. And this way you can compute like sort of the quality of the clusters in the embedding space. That is to say, a text encoder that correctly understands the medical content should be able to clusterize nicely in the embedding space reports that are describing the same abnormalities. And so that's what we compute with this Chexpert at K score. That's the ability to correctly clusterize together in the embedding space impression sections that describe like similar symptoms or abnormalities. And so using that, we can like, for instance, for each text encoder, and like different extraction method of these embeddings, we can compute this Chexpert at K score. The higher, the better. And therefore see, that's maybe a detail, but that was like interesting for like the rest of the project. See that like different extraction methods lead to different performance. And so most of them, for instance, if you want to learn a good document level representation, you would use like the CLS hidden state. But sometimes like pleural output could be better. That's the case, for instance, for the clip text encoder. And look for the clip text encoder, for instance, the CLS in state is super bad. Like you should not use that. But yeah, just a detail, but it affects like performance. So that was like interesting, like to explore that. And then, so let's say, for instance, for each text encoder, we use the best extraction method. We were then able to compare them to each other and see which text encoders are best at understanding, well, the medical content of impression sections. So we can look like at the Chexpert at K score per abnormality, and also we can have like a macro average. And what you want basically is to always have like the higher scores, which means that the model like correctly clusterize similar abnormalities together. And well, if we look directly at the macro average, we can like, and so in each column you have like different like text encoders. You would have, for instance, this one, which is like the Mimic CXR specialized model of Microsoft. This one is the one having like the best macro average Chexpert at K score. So given this metric, the one that is best at representing medical content that is in text prompts. But a very interesting finding is that the clip text encoder, which was trained on this general domain data, has like a score of like almost like 53, which is similar, if not higher, compared to all the other domain-specific text encoders. So, well, for instance, it's quite similar to Radbert, which is also a model that we released recently, but okay, we are beating like clip by a tiny margin, but yeah. But it's better than, for instance, Clinical BERT or PubMed BERT and so on. So interesting finding. And that's also like a good thing because it means that clip text encoder is not that bad. So maybe we can like, if we want to have a stable diffusion model that we further train for the radiology domain, maybe that means that the clip text encoder can be kept frozen. The variational autoencoder, as we saw, can be maybe also kept frozen. And maybe we just need to leverage this unit in the middle. So that helps us like better assess what are our options. And just looking at like some visual assessment, what you could also do to evaluate all of these things is feed this representation to a TSNE, get visual representations. This one that would be like TSNE projections of all the impression sections. The colors correspond to different abnormalities. So you would see here that the colors are not super well clustered. This representation is bad. These one, for instance, are better. So you can also like compare. So here you have all the pink together, the red there, the yellow there, the green there. Here it's more difficult, but you have better clusters. So that's also another way to assess all of that. So we saw that the clip text encoder is not perfect. One way could be to keep it frozen, maybe leverage the UNet. But another way could be maybe let's not touch the UNet and only train the text encoder. That's like our options that we have on the table. Just to give like a quick overview of what we can do to further train the stable diffusion model for the radiology domain by only training the text encoder part. What we can do is either like the textual inversion approach. So just to explain, like, so we have like this text encoder. We know, for instance, clip text encoder is good, but not perfect at understanding medical content. Maybe what you would like to do is to avoid retraining it on the medical field, because that's not perfect. And also that's going to mess up the embedding space. And so if you keep then the UNet and the variational and autoencoder frozen, things won't be aligned anymore. And that's not going to work for the generation, for the stable diffusion generation. So what you would like to do in this case, if you only want to retrain the text encoder area and not the UNet and not the variational autoencoder, is do this textual inversion approach where you add a new token to the vocabulary of the text encoder, and you basically keep all the text encoder frozen except the embedding of this token. So you learn only this embedding of the token. The advantage of this approach is that the embedding space of the text encoder stays the same. So if you then like use these embeddings to make the UNet attend it and then generate like images, the UNet won't be like lost. Like the structure of the embedding space will still be the same, but you'll add like a new token. So you're basically learning like where is this token in this embedding space, and then the UNet should hopefully understand this new meaning, this new concept. And so with this textual inversion approach, you could introduce the concept of pleural effusion, for instance, and try to learn this concept. And then having kept like the variational autoencoder and the UNet of the stable diffusion pipeline frozen, hopefully get images that are more, that look more alike and like radiology images. Another approach, we could discuss about that like for a long time, but would be like textual projection. So you have the original text encoder, which is a clip. This clip text encoder has a certain embedding space, and that's like with this embedding space that the original stable diffusion model was trained. So so the UNet especially understand the structure of the clip text encoder embedding space. If you want to switch this text encoder with another one, let's say like a domain-specific text encoder, well, the domain-specific text encoder will have like a different structure of the embedding space. So if you just switch the models and then like ask the UNet to generate a new image, like he will get like a condition on an embedding space that he doesn't know and that has like a different structure. So that wouldn't work. So what you would like to do maybe is if you want to switch the text encoders, add a small layer that can be like a linear projector that tries to align the embedding space of the domain-specific text encoder with the original embedding space of clip. And so training such a projection, but not too much because you don't want to erase also the domain-specific knowledge of this new trained text encoder. But yeah, training this kind of projection to make like embedding space more aligned and then be allowed to switch text encoders could be like an approach to keep the variational autoencoder frozen, the UNet frozen, not really training any text encoder, just retraining like a small projector, and then being able maybe to generate medical images. That would be like this approach, interesting to investigate, and yeah, also by itself, you know. So that's like what we can do in the trained text encoder part, at least what we thought of. I'm sure there are other ideas, of course, but yeah. So last element that we can leverage if we want a stable diffusion model that generates like better medical images is to leverage the units in the middle. You could keep like the variational autoencoder frozen. The text encoder, the clip one, we saw that it's pretty good at medical, at understanding medical content. So maybe it can be kept frozen too. And you can just like further fine tune the unit. This approach, there is one paper that already investigated that. It's called DreamBooth. Well, it's just like a basic, well, it's called DreamBooth, but it's just like unit fine-tuning. DreamBooth like investigates especially the few shot learning setting. That is to say, you fine-tune only on a small number of images that are like domain specific. And as Stable Diffusion is like a super powerful model, in fact, seems to work. So you can like retrain on a new model, like on a new domain by fine-tuning only the unit and having only like a few data points. And that could work, and that's what the DreamBooth paper shows. So that's what we also wanted to investigate for this paper. So we have all these methods, some methods that retrain some parts of the text encoder, textual inversion, textual projection. We also have like the DreamBooth approach that tackles the units. How do they compare? And do we have like good in-domain images? That's what we were hoping for. So if we do a visual comparison, maybe like more effective than metrics, let's start maybe with that. We have, so we tested like with two basic prompts, a photo of a lung X-ray and a photo of a lung X-ray with pleural effusion. The goal of the first prompt is very naive, and it's just to show like, is the image, does the image look like a chest X-ray? And the second image would be nice if on top of an image that looks like a chest X-ray, we have something that looks like a pleural effusion symptoms. That would be like an even better thing. The original model, well, the original Stable Diffusion, well, it looks like like lungs, but that's not really like a chest X-ray, even for someone that is not a radiologist at all. Textual projection. So we investigated that. We try like several like projectors, and that's quite tricky to align like embedding spaces, because like all these text encoders, they have like high dimensional embedding spaces, though it's like much smaller than the vocabulary. It's like 768. So it's quite tricky. And so we can always give more details, but like trying like an approach that does not like take too many training steps with like not a super huge training data set. So, well, I wouldn't say like a fusion learning approach, but yeah, like a quick approach, like to train a projector to try to approximately align embedding spaces. And then leveraging that to switch text encoders. Well, it didn't work well. We lost like the meeting. In this case, the document that was like one of the approaches to train the textual projector. So the document level, we even lose like the structure of the images. The token level, we don't lose the structure of the images, but they are like out of context. That's not what we wanted. So that part, we didn't like it. The other part that leverages the text encoder is like token embeddings and the textual inversion approach. That's correct. So we have like an improvement of the quality of the images, which is nice, especially here. We do not really see like the added value of pleural effusion, and also like anyone without being a specialist can still say that's not an X-ray image. The thing that ended up working super well is like to keep the text encoder frozen, and clip works well, so we were happy with that, and to train only the units. And so training the units seems to work. You can play with priors to do not forget knowledge. So for instance, you would maybe try to learn first during a first step, like the radiology image, what it looks like. Keep that as a prior to then further train to learn the pleural effusion itself. So you could do that. And it seems that we have, so we can still like guess that they are like fake and synthetic. But for instance, we see like some sort of a pleural effusion here. Especially here, when we use like a prior, we have like well a vanilla chest X-ray image, and there you see the addition of pleural effusion, what it does, and starts to look like yeah, like the symptoms. And you can say that when you compare these two images, here you have pleural effusion, whereas here you don't have that. And so that was like the nice finding is that like this approach, UNet, and like incorporating priors was maybe the best way to go if we want any domain stable diffusion model. We can further like explore like the generation capabilities, like comparing these prompts. These would be like on the left, the original images, and on the right, like generated images. And yeah, you clearly see the difference between like a no finding image on the top and on the bottom, an image which is supposed to show like pleural effusion symptoms. So it was a very good sign. And up here, that's Chris that was able to generate such things, which it looks amazing. So you see like, you know, the denoising process, which makes like a stable diffusion work, and really like how from random noise, it iteratively adds like some meaning that is conditioned on the prompt, and to end up with something that looks like a chest X-ray. It's like super nice. Yeah, and here you have a small comparison, but yeah, very happy with that. That was a nice finding when we got that. And then, so we just tried at the end to quantitatively like assess and compare all these things. A first approach was to use like the FID score, where we compare the distribution of true chest X-ray images, whether like they have like no findings or maybe pleural effusion. This true distribution with distribution of synthetic images, and you use the FID score to assess whether they are like alike or not. Lower FID score means it is better. And like using this score, we get in fact like the smallest scores. We get them with the unit training, which confirms the visual assessment that we had. And another way to assess like the quality of these images, more like in terms of like medical correctness, is to use like a vision model that is trained on chest X-ray images to output the expert labels. So a model that can say, okay, this chest X-ray images is no findings, this one is like pleural effusion. So you have this model and you can feed synthetic images that are like conditioned either on no findings or pleural effusion. And what you are hoping for is to have like the images that are like supposed to have pleural effusion should be like labeled as having pleural effusion. And that's what you can measure with like such a dense net model on top of these synthetic images. And in this case, what you want is a high AUC, that is to say, for the synthetic images of this model, the dense net almost always have the right answer. So the synthetic images that are supposed to have pleural effusion are detected as having pleural effusion. And the ones that are supposed to have no findings are also like labeled as no findings images. So yeah, so two things that we investigated and that like confirm our visual assessments about the quality of the images and also like the correctness of their medical content. And with all of that, we were super happy and also happy to answer any questions. And yeah, we had like some images that look like radiology. So that was a nice, nice finding. Yeah.
Awesome. Thanks, Pierre and Christian. I think that was a great talk, and it's really exciting that stable diffusion can be used for radiology. So I guess before we move on to questions, we can just give a round of virtual applause for both of you for the great talk. And yeah, and now I'll leave the floor open for questions.
I guess I have a quick question. So you showed that, I guess the classification between plural or not was pretty good. Have you tried using the actual images and like augmenting tasks?
Oh, so you mean like using these synthetic images and see if they are like good data augmentation tools?
Yeah.
I think that's one of the objectives to show that, like thinking of like so we didn't try in this paper yet, but we are like highly interested in that, of course. And yeah, that's like one of the immediate applications, like, well, beyond like it's nice images and so super cool to play with the model beyond like that thing. That's probably one of the immediate next steps, to be able to show and leverage these models for like data augmentation purposes. And for instance, on a task such as like the check per task, you would like images that are rare with fracture, for instance, and at which like the current expert models struggle. You would like to be able to data augment them with Stable Diffusion and hopefully have models that are better at detecting rare diseases. So that could also like improve fairness, which is a super nice thing if it works. Yeah.
Thank you.
Oh, I see Eduardo. Yeah, go ahead, Eduardo.
Thank you. Congratulations for the work and for the presentation. Thanks so much for letting us know the details of that. It's super exciting. And just following up on these questions, just pop up on my Twitter a paper today that shows on OCT, ophthalmology images, that synthetic data works as well as normal data for this specific task, OCT. For training classification. So I was going to ask Christian about the motivation and the context of these that you were talking in the beginning. So it's really hard for share data between institutions. So are we going towards a world where instead of sharing data or doing federated learning, are we kind of using synthetic data for everything?
Yeah, so I think I spoke in the beginning about a few points that motivated this project in the first place. Well, apart from playing around with a cool new generative model, of course, you eventually want to do something with it that makes sense and that adds value to this domain that you're applying it to. And one thing, as I mentioned before, is definitely, as you mentioned, multi-institutional data sharing and collaboration. As you already mentioned, federated learning is one way of doing that, but you can also see synthetic data as being shared as an option. There has been very recent work where a latent diffusion model has been trained to generate synthetic brain images. And they released a big data set of synthetic brains. And from the same group, they also originated some work where they train a segmentation model solely based on the synthetic images. Very exciting application scenarios, and I can definitely see it happening. For me, when I think about this, is like creation of synthetic images are just another tool that you can use to collaborate in that space. I'm not saying it's the only solution, but I mean it's expanding the toolbox that you have at your disposal.
I see that Iman has a question. Go ahead, Iman.
Yeah. Hi, thank you for presenting the talk. And I have just a few questions. First one is that what text encoder you use for that? Is it clinical bot, biobot?
Oh, so we ended up with the approach that works best. So fine-tuning the unit, therefore keeping the text encoder frozen, and that's clip. And
Clip, okay.
Yeah, that's
because
fine
because the main typical problem that we face with clinical vocabulary is that most of the words are not present in the vocabulary, so we have to split the words. For example, like pulmonary embolism, we can clip the word as pulmonary and embolism separately, and sometimes it's confusing and it creates a different types of diagnosis, so I don't know if you guys think of like training a transformer model from scratch and then learn the vocabulary on the gest texture domain itself and then run the model on that, because your actually model highly depends on the diagnosis. Even forget about the lung image or lung gest texture, that part of the text, but at least the diagnosis part is pretty important for you.
But the clip text, so clip text encoder, it's not ideal. And at first we thought, okay, it's trained like on general images, it will be terrible at domain-specific images. But like even compared to transformers that were made for this domain, such as PubMedBird. So PubMedBird doesn't have like a radiology vocabulary.
Exactly.
Like,
PubMedBird, like all of these ICU, like mimic dataset, they don't really have the radiology vocabulary. So
PubMedBird has the medical, biomedical vocabulary.
Yeah,
so
but still most of the radiology words are missing from there.
Yeah, but like clip like benefits anyway from like the tokenizer, like splitting the words into subtokens, and it learns like representations for these subtokens. And then that helps, like, though the words, the entire words by themselves as not directly part of the vocabulary, the subtokens are. and it learns like representations of these subtokens. That makes sense. They are probably not perfect, but we are able like to then use such text encoder to condition on medical content.
Exactly.
And
So
the
my
narration-
question is that why do you need the text? You can just put the diagnosis, right? And you can just tokenize the diagnosis and put the diagnosis itself on the
so you
VA.
need that.
Yeah, why do you need, because lung chest x-ray would not be different, right? Because you are only training the model on the chest x-ray, so it should generate only chest x-ray. So the language is not that important for you. The most important thing is like categorization of the conditions of the diagnosis.
I think the obvious like
Sorry.
you know, you want to go ahead, Chris?
No, if you're speaking about the setting where you have class conditional model.
Yeah, class conditional VA, yeah.
And what I think this, like what we try to show is a transition towards a more densely conditioned model instead of a sparsely conditioned one.
But have you ever used like multiple conditions together? For example, like a patient with cardiomegaly and pneumonia in the same sentence.
So we are currently working on that, combining
Okay.
different pathologies, and we are making some progress with that. It doesn't work very well off the shelf, to be
Right.
to be honest.
Right. Because
So-
I personally believe, like, I don't know, it's you guys worked on that, so you guys know probably better, but I personally believe like if it is a class condition and you use the fuzzy conditions of the labels, it will work better than actually encoding the text.
Yeah.
It should work, yeah.
The
Also,
goal
in the few shot setting, of course, you have the problem that when you try to add a pathology, then it forgets, or it
Right.
tends to show forgetting. Yeah.
And as Chris said, like the goal of this work is really like to open like the conditioning to like a dense space of potential prompts. And we want to first show that on vanilla prompts that could be like modelized by just like a few number of classes, that on vanilla prompts we can learn something, and then of course like enlarging that to like a wide range of potential medical prompts. But that
So
was
when
like, yeah.
So when you train actually your diffusion model, did you use any data where you have multiple labels for the single images? Because Mimic has the multiple label for single images.
No, like, so this approach, like, so all this work like was like quite like in the proof of concept
Okay.
stage. And so we were like starting like simple, just to see if only like simple things can first work. That was like not given, and we were not sure about that. So we tried like on like no findings images only with pleural effusion, images only with cardiomegaly. Does it work on that?
Okay.
So yeah, then of course like there are a lot of applications. We're pretty sure. So
Okay. Thank you.
thanks for your question.
I have a question about like how realistic are these generated images? Do you ask the radiologist to look at them, and like are they able to distinguish which are the real images and which are the AI generated?
Yeah. So fortunately, I am a radiologist, and I do that myself. And to be honest, because during your residency, you typically see tens of thousands of images. So it's very hard to create something that is really with high fidelity in every aspect that you could potentially look at, realistically looking. But I have to be honest, it's getting pretty close to the point that you need to look at it for a couple of seconds to make the decision whether it's true. So in the first few attempts that we did, it's very like just a split-second decision where you, for instance, you see a wrong number of ribs, or you see some anatomically impossible features in the image, and even though all like the shades are correct, and like the general shapes are okay, the thing about radiology is that sometimes it's very small local features that decide between a pathology and a healthy patient. And so it, like, the generative model needs to get a lot of things correct. That being said, it's moving to a point really where you need to look very closely, especially like one thing that the models struggle with is devices. So when you have a lot of wires in the image, at some point they tend to be discontinued or something, and that's a pretty strong sign, for instance, that this is a generated image. But if there are no devices in there, and it's a chest X-ray image without any findings, it can be quite hard to distinguish it.
Sounds good.
Yeah.
Yeah, that's all. Thank you.
I know we are kind of like over time, but Chris and Pierre, do you have like a few more minutes for questions, or?
I'll be happy. Yeah,
Of course.
no immediate meeting after this.
Okay, cool. Yeah, so I guess folks who have to leave, please feel free to drop off. But if you have more questions or discussions, feel free to hang around. And I guess I can get started with one question actually. So with a single prompt, if you generate multiple images, how different are the images? Like, let's say you have the same, like you give 2 examples of the prompts. So how, like, did you actually find many instances of chest X-rays with pleural? I forgot the exact term, but like that condition. So I guess.
For effusion?
Yeah.
Yeah, so I mean, in the few shot setting that we explored for this project, the variability, especially of the pathologic images, is, I mean, there is some variability, but it could be higher, to be honest. So and that's one thing that we're definitely working on, to increase the diversity of the generation, because that's one of the 2 major quality criteria that you have for generative models, is one being of high fidelity and the other one being of high diversity. The images still look pretty variable, because it doesn't only change the pathology, but also it changes the whole, basically every aspect of the image. If you took a look at the GIFs that we included of this whole process, every image is sampled at a different time step, so you can see that progressively it doesn't only work on one aspect at a time. Everything is like wobbly and changing and slightly different. So while the general aspect of the image may not vary that much, the smaller details do, a lot of the time.
Interesting.
Yeah.
Cool. Thank you.
And just to add, but as a non-radiologist at all, I struggle a lot at understanding if it's correct, not correct. So yeah, like I think we are. Yeah, that's also like a good sign that now we need like radiologists and so on to assess in depth, like where are we in terms of performance, and are there still a synthetic or very real? Yeah.
Absolutely. And I guess if you had to take this to a different medical domain, like let's say like ophthalmology or like brain scans or something, what would your recommended pipeline be? Like how should one practitioner actually do something with?
I think the experiments that we did are pretty much transferable to any other medical domain. First, see how well the latent space preserves the features that you're most interested in. I think you should work with some kind of domain expert on that to see that the fidelity is high, and all the relevant features are being preserved. And then I mean, my guess would probably be that for the text encoder, it's the same thing. It's not optimal, but you can probably start off trying to keep clip frozen and try to, if it makes sense and works with your data, or you could just not use clip and just try to class condition your model, like Iman suggested. And then I think the trick really is to try to fine tune the UNet in the few shot setting. To be honest, it is not even the case that you need a very powerful hardware. So you can play around with that if you have a MacBook or anything with a decent GPU. You can try to play around with that, and probably if I were to test this out on a new modality, that would probably what I would try to do first. So first look at how well are the images preserved, and then start fine-tuning the unit.
Just about like the text encoder, well, clip first is quite good, surprisingly good, but it's not also like the end of the world if the text encoder is not super great at understanding. Well, of course it helps if the token representations are good, but well, the UNet on top of it, though like the token embedding is not perfect, the UNet will by being trained, understand that this token in fact is like the medical thing. So you will end up like working on like the model is like so powerful and so good at learning things that it can like, we have the impression that it can overcome like these things. Yeah.
Awesome, thank you. Are there any more questions from the audience? Well, I guess if not, then we can kind of end for today, but I'm sure like this is the starting point for many more discussions. So if you have more questions, feel free to reach out to Christian or Pierre or get in touch with us, and we'll put you in touch with them. And we'll have the video up on YouTube as well today. And yeah, see you all next week. Thanks for joining today.
Thanks for having us.
Thank you, Pierre and Christian.
Yeah.
Yeah.